All right, we're back for more. So, just wanted to work through a couple of problems with you guys again and kind of talk you guys through some things here and, give some comments about things. So, again, here's your opportunity to stop and write down the question and see if you guys can work through it before I start talking through it. So, now this question here is actually interesting because I'll have to admit, right? I have to admit, the question asked, come up with a simple or a straightforward. I believe the wording was come up with a straightforward synthesis for this transformation, and I came up with something. And I'm like, man, it's just just wasn't very elegant, right? It took a lot of turns and it took quite a few steps. I got there, and I was like, I just don't like that, and so I had to sit there and I had to think about it. And I'll admit, I had to look up the answer. I had to look up the answer to come out to see, what an elegant solution was, and I'll tell you why here in just a second. But anyway, we'll get to that, right? So let's see what's going on here first, right? So first things first, right? We got an aromatic ring. So as soon as we got an aromatic ring, you guys need to kind of load in all your information there about dealing with aromatic rings and the reactions and all that kind of stuff. But taking a closer look, what we notice is we're really not doing anything with the ring itself. We're doing stuff with the side alkyl chains. Okay, so that means that while we do have to keep the aromatic ring stuff in mind, we kind of have to bring in our, for lack of a better description, our organic one mindset. Because the organic one mindset is where we dealt with everything not on an aromatic ring, if we want to be very general with it at the moment. I hope that kind of makes sense, right? So we have to understand what will react with the ring and what will react with the alkyl side chain off of the ring there, okay? But there's something else that's important, right? And this is where it gets tricky, right? So we see that if we start to go in and just kind of look and count carbons, we see that we have to basically lose a carbon before we get to the end there, right? We have to lose a carbon before we get to the end. And so that's kind of, that's a challenge. There are just a couple of reactions that we know that can actually do that. And I'll tell you the trap that I fell in when I was going through this problem here. I'll tell you guys about it as soon as we kind of get a little bit further along here in the walkthrough. But being able to take a single carbon off of a compound and kind of add an oxygen in its place, there's not too many reactions that we know that did that, right? And so that's kind of where I got tripped up when I first went through and did this. And especially coming out of the chapter that these questions are in, right? That is, the aromatic chapter. So there were, that might be a little bit of a sticky point there. So if you guys, took some time and you stopped and you tried to work through the problem, but you couldn't come up with an answer. So think about that. The answer to get to the, let's say, elegant solution, right? The simple solution is going to take something outside of chapters 17 and 18, right? I hope that makes sense. So try and think of something that's outside of chapter 17 and 18 here to come up with that answer. How we can chew away one carbon and leave an oxygen in its place. Okay. So for those of you guys who are still, with me, all right, let's go through it here. The first thing to notice is we don't have a functional group on our alkyl side chain. So first things first, let's add ourselves a functional group. So we'll radical halogenation it up here. So a couple of quick thoughts. I know we talked about this in lecture, right? But that purple carbon there, that's a special position. That's a benzylic, right? That's our benzylic carbon. That's where our most stable carbocation would get formed. Our most stable radical would get formed. In this case, right? If it's a tertiary benzylic position, that's a very, very, very stable radical and carbocation compared to other ones. So there's that. So now that we have a functional group, we're going to have to now that we can do stuff with it. Now, here's what we're going to do, right? So what I'm going to do now is I'm going to go ahead and eliminate, okay? And we can pick, whatever strong base that we want. Sodium ethoxide would be just fine. We got a tertiary, right? We got a tertiary leaving group there with the bromine. We're not really going to have to worry about substitution, right? Even though we can generate a stable carbocation because it is radical, remember that's always going to be our rate determining step, is to generate that radical, generate the carbocation. Right? Even though we've got a tertiary halogen there, generating a tertiary carbocation is not easy to do, even if it is benzylic. It's easier to do, but that's all relative, right? What does easier mean? Well, it's just easier, right? So anyway, all right. So we can pick a base. You guys could pick a bulky base, something like T-butoxide LDA would be just fine too, but sodium ethoxide, no problemo. Okay, so we go through, we do our E2 elimination. All right. And so then we'll leave behind, oops, sorry, no, that should be in green. I got a little bit ahead of myself there, that's okay. All right, so we leave ourselves a double bond, okay? And so now I have to call you guys back to my hint that I gave you guys about how to do this, or how to affect this transformation. How can we turn an alkene, right? How can we turn an alkene into a double bond O? And so there's a reaction that we learned, and really this is where I got tripped up. There is one reaction that we learned how to do this. Okay, there's one reaction that we learned how to do this, and that's our buddy ozonalysis, right? So ozonalysis is where we have ozone, and we put that ozone over, we bubble ozone through our solution, and then we add something called DMS, which is dimethyl sulfide, right? Dimethyl sulfide, and dimethyl sulfide helps facilitate the, the transformation and clean things up, okay? But if we do that, if we do these conditions, right, that oxygen right here is coming from the ozone. And so let me just, this is something I would introduce to you guys in the first semester, but this is what we call what I call, right, this is not something that's in the textbook, the snip, slide, and slap, right? So what we do is we snip that bond right there, right? So we snip that bond right there. So if we imagine just kind of physically cutting that bond in half, right? And while I'm drawing this out, I give all credit to my undergraduate organic chemistry teacher for teaching me this. I'm not that old yet, but it was quite a few years ago where I took OChem 1, and this still stuck with me through today. So this is a quick shout out for Dr. Sandberg at North Carolina State University. She was a fantastic teacher for organics, so it still stuck with me through today. So that's her idea here, right? The snip, slide, and slap. So what we do is we snip the double bond, we slide them apart, right? So if we're doing ozonalysis, we snip it, we slide it, and then we just slap an oxygen in the place of where we cut that bond, okay? So here's the tricky part, right? So what we had left over, oops, I shouldn't do that in purple, excuse me. Let's do that in black. So one clue would have been if I would have shown you guys that we made this product along the way also, right? That would have helped with this. But ozonalysis can cut a double bond, right? So we can break carbon-carbon bonds, and we can put an oxygen in place where we can cut those double bonds. Now, what I had originally gone through, I'm not going to go through the whole thing, right? Well, what I had originally gone through was, what I'd done is this, and I went through our alkyl oxidation. Remember, if we take some permanganate or some chromium and we heat this up, we can completely chew off our alkyls and leave a carboxylic acid in its place. And then I had gone through and brought in a organocuprate, a Gilman reagent, and done this transformation. But that's not quite, I don't think we have all the reagents to do that yet. That's going to be coming up in the next semester. Yeah, right. In the next chapter is what it is. And so this why I am introducing this here now is just we will learn another way of affecting this transformation. Okay? And so there's going to be some reagents that we can learn there to kind of do these transformations and come up with a different method rather than using ozone to come up with this. Okay? But at the end of the day, right, so this right here, we'll probably come back to this problem in one of the future problem sets once we have that other set of reagents that we can do this. But what I did want to do is just recall ozone is something that we can use, not too common, and it's a very unique reagent that we can use to cut carbon-carbon double bonds. Okay, so hopefully that kind of knocked the rust off like it did for me there. Hopefully now you guys remember your stuff about ozonolysis there also. All right, next problem. Okay, so again, stop, try and do it for yourself, and then let's see what happens. All right, so we are working on an aromatic ring. And now we're actually adding stuff to the ring. Okay. So we start with an unsubstituted ring. And at the end, we have to add an alkyl group. We have to add a halogen. And we have to add an amine, right? So the amine and the alkyl group there are para to each other. And the amine and the halogen are ortho to each other. And what I'll pause and say here is that when this is a very typical question, right? You guys can pretty much almost expect something similar to this to be on the exam just because this involves a lot of the concepts that comes out of it, right? So kudos to me for picking a great problem. All right, enough of that. So what I'm saying is the first thing you got to do is assess the relationship of everything to each other, all right? The other thing you have to do is assess how each of those groups affects the ring, okay? What I mean is this. Our amine, right? This is an activator, okay? Our alkyl group is an activator. Our halogen is a deactivator, okay? Now remember what we talked about activating and deactivating. We're talking about actually letting the reaction happen, right? We activate the ring towards electrophilic aromatic substitution, okay? So what I mean is this. If I have a deactivator on my ring, I can't, it's going to be really difficult to add something else to it, right? Because the ring is deactivated, right? You guys catch that? This is important, okay? If we put a deactivator onto the ring, it's really hard to do the next reaction. I hear what you guys are saying, right? But Dr. H, you tell us that everything, right, that chemistry always works on paper. I do, but remember when I say that, what's implicit is that we can't violate the rules, right? Chemistry always works on paper. We don't have to worry about cleaning things up and extractions, right? But we can't violate the rules, right? We can't just poof something into existence and violate the rules of organic chemistry. Got it? So what I'm saying is, what you should do whenever you see a problem like this is look at the relationship of everything in there and take a look at what's an activator and a deactivator. Because typically the deactivator has to go on there last, okay? Because if we put a deactivator on there, right? If we put a deactivator on there, it's going to really slow down the reaction. Unless the ring already has an activator on there to kind of balance things out. Here's what I mean, right? So let me stop talking and let me just put something into words real quick. Okay, I'm just giving an example. Okay, let's say I wanted to do this reaction here, right? FeBr3, and that seems fine. Okay. Essentially, this would really not give a reaction, okay, because this is a deactivated ring. Now, if you sat here and you maybe waited for 3 weeks and, you kind of heated this up and let it do its thing, it might end up doing something. But because the NO2 group is a deactivator, it's really going to slow down electrophilic aromatic substitution to the point that it will not react in some cases, okay? That's what I'm trying to say. However, right, if we had something like this, for instance, okay, so this anisole derivative, this is a good activator, and then we could get this reaction to work, right? Then we could probably come in, and we would end up with a product that would look something like this. Let's get some colors here. Got it. So the nitro group is going to deactivate, but we do have the anisole there, the methoxy derivative, the ether, which is a strong donating group, which will activate the ring towards electrophilic aromatic substitution. Does that make sense? So it's a balancing act, right? That's all I'm saying. All right, let's clear some space. Okay, so let's get rid of this. All right. So let's just make a quick note up here, right? Examine ring. We'll look for ortho, meta, para relationship, right? OMP, and activators. Deactivators. Good. The next thing we have to look at is, how do we want to put this? Let's say structural features, okay? So what I mean is this. Take a look at this alkyl chain here. It is attached to the ring through the terminal carbon of that chain, right? So that is that purple carbon, right? That purple carbon there was a primary carbon with a halide on it. Okay. All I'm doing is kind of, cutting that chain off and saying, remember, we have to bring in an alkyl halide or an acyl halide to be able to add this to the ring. That makes sense? I'm assessing how my alkyl chains look, right? So alkyl chain connections, right? So that means since my alkyl chain there got added through that primary carbon, that means I would have to do my acylation in this case, okay? So what we're doing is I'm just assessing the acylation versus alkylation, okay? And we know both of those mechanisms. We talked about it, all that kind of stuff, right? Cool. The next thing to do is recognize when we have an amine, right? Amines can be added two ways. The amines can be added either through electrophilic aromatic substitution of a nitro with a reduction to an amine, or they can be added through the nucleophilic aromatic substitution, typically through some kind of benzyne mechanism. Now, truth be told, right, it's far easier to go through the nitro than through the benzyne derivative. Not necessarily for any particular reason aside from the conditions for the benzyne are pretty harsh. They're strong bases. We have that problem of scrambling, right, where we can add things to two carbons that are in there and kind of make our yield less than what we want, right? So all I'm trying to say here is if we have an amine, right, that typically means nitro reduction to the amine. Okay. All right. So now that I think we've kind of gathered as much data as we can, let's start to work on this here. Okay. So the first thing I'm going to do is I want to add an activator to this ring. Okay. The first thing I always want to do is add an activator to this ring. Now, my halogen is a deactivator. I'm assuming I have to go through the nitro here, and that's a deactivator, right? So the nitro and the halogen are deactivators. So the first thing I need to do is add that alkyl chain. Okay, so let's add that alkyl chain. So we got 4 carbons in a row, 1, 2, 3, 4. I'm going to set up my acylation, right? There it is. Right? So for those of you guys who are paying particularly close attention, what you'll notice is I do not have an activator on my ring. A ketone, a carbonyl, is a deactivator. Okay, this is a deactivator actually. So now we have to go back and get rid of our ketone. Do you guys remember how to do that? So this is our reduction, right? So what we want to do, right, is take our zinc mercury amalgam, so ZnHg, right, zinc mercury amalgam, and some HCl, and we typically, heat this up or something, but that's just fine. And when we do this, now we get rid of our carbonyl. Oh no, I ran out of space. Nuts. That's okay. Right, and when we do that, we get rid of our carbonyl, and we're just left with an alkyl chain there. Alright, so now we have an activated ring. So this is an activating group, right, our alkyl group there. It is also a fairly bulky group, which means the next thing that's going to come in is going to be added para. Well, from our answer, we know we have to add that amine there, and we're assuming we have to go through the nitro, so let's do that. So HNO3, H2SO4, standard nitration. Nothing fancy here yet. All right. So now we have an activator and a deactivator on the ring. Fair point would be to say that this is probably a more deactivated ring. Nitro groups are very strong deactivators. Alkyls are only moderate activators at best. Although we're kind of hand-waving a little bit of maybe some concepts here, but that's okay. But let's pause here again. So now we have two things on the ring. Where will the next thing be added? Well, this is an ortho-para director, right? Well, the para position's blocked by the nitro, and my ortho positions are here, right? Cool. My nitro group here is a meta director. Where are my meta positions? Aha. So kind of now we've set up a situation where we overlap our ortho and meta directors here. So let's go ahead and add our halogen then. So we'll come in with our typical halogenation, Br2, FeBr3. Probably would be a somewhat slow reaction, but this is still fine. We've got an activator and a deactivator on there, and we're still good. Now the last thing we got to do is convert the nitro to the amine. And all we need to do in this case is we either take zinc and HCl. Right? We either take zinc and HCl, or we could take iron and HCl. Is a perfectly fine way of doing this also. And now we've got to be careful. So we got to pause here for just a second, okay? So if I just put zinc and HCl in there, I will reduce my nitro to an amine, but we're under acidic conditions, okay? We're under acidic conditions. So what do amines do under acidic conditions? Well, they remain protonated because they are bases. So we always see this finished up with some kind of aqueous hydroxide workup here, okay? And that'll take us to the amine that we want. And this is an aqueous workup, and we're good to go now, okay? So a very classic example here of adding multiple things to a ring. We have to consider the orthometa-para directors, whether they're activators and deactivators. When we're going to add each of those to the ring, we typically want to add activators first to kind of get everything else on the ring, right? We have to pay attention to alkyl groups and how they're attached. How do we add amines? How do meta directors and orthometa-para directors work together? All this kind of stuff that kind of goes into this problem. So I really do like this problem. So this is a good one to stop, go back, and see if you can rationalize your way through this also, okay? All right, and so I know there's a couple other examples about very similar to this in the book. So please, please, please spend your time to go practice with that, right? I'm looking at page 825. Right, 825 walks you through another very similar example to this, right? So take a look at page 825 there, right? Kind of walks you through another example. All right, so that's it for this problem set here. I'll see you guys on the next one as we keep kind of working through and, working some practice problems here. Again, as always, if you have any questions, please don't hesitate to reach out.